to the heat of your body and the heat of the sun, and that makes it bigger, and then it's hopefully then easier to slide back off. But at the same time, your finger being warmer also means that your finger expands, so that can become kind of a complicated issue. But that's one place where some people tend to notice it. If you've ever thought that your ring was harder or easier to get on or off, when when there hasn't been a reason that you could think of for that, that's likely why. Just thermal expansion. Things that are warmer just are bigger because of thermal expansion. But there's another place where you've probably seen something about this, and it's on bridges, actually. If you've been driving over a bridge or just in a vehicle as it passes over a bridge, sometimes you might notice as you're driving and feeling kind of the car bouncing up and down kind of rhythmically, ka-kunk, 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 and you notice these metal spacers in the roadbed of the bridge. These things exist because of thermal expansion. Bridges absorb a lot of heat during the day. They are in direct sunlight. They are made of stone, so they absorb heat and they hold on to that heat pretty easily. So bridges will expand thermally as they warm up. They go through a pretty sharp temperature change between the cold of the night and the peak heat of the day. And that means that the concrete roadbed will get longer will be longer on the hottest summer day compared to it being shorter on the coldest winter night. And since that roadbed will inevitably change size, you need to install spacers like this such that when it expands, the spacers have room to expand into each other, and when the bridge contracts because it's colder, those metal teeth still form a surface that you can drive over. If you didn't have these here, if it was just one solid, uninterrupted piece of concrete, the whole thing would expand in the heat of the summer and then press into the ground on either side of the bridge, and that would just push on the bridge inward more than it would normally be used to, and this tends to result in the roadbed cracking. A surprising amount of damage to the roads anywhere is just due to thermal expansion. Even normal non-bridge roads, the concrete absorbs heat during the day. If it doesn't have room to expand, it's going to expand. If it doesn't have room to in a way that relieves the pressure from it expanding, it's just going to crack. So that's thermal expansion becomes a surprisingly dangerous thing when ignored in the fields of construction and civil engineering. Architects deal with this too, because technically, on the hottest day of summer, the Empire State Building is taller than it normally is on the coldest day of winter. And if your building isn't designed to deal with the shocks and the pressures of various parts of it literally changing size, things will crack and fall apart, and worst case scenario, your building falls over. So, surprisingly very important, and surprisingly very catastrophic if ignored. All matter does this, solid, liquid, and gas, all three stages. And tapping back a little bit to look at the formulas for this particular concept. When something gets warmer, it will expand, and it will do so both linearly in terms of how long it is, but it will also do so volumetrically. It will get bigger in all of its dimensions. So not just longer, but also taller and wider. Because it will expand in more than one way, we have two slightly different formulas to describe the linear expansion versus the volumetric expansion. But they're very similar formulas that operate on the same logic. We're mostly going to look at the length one right here, but I will explain some of the differences. Please cut me off if anyone has any questions thus far. So, This here is the formula for the expansion, the thermal expansion of an object. The formula is delta L, that is its change in length, divided by its original length at your starting temperature, is equal to alpha, which I'll explain in a minute, times the change in temperature of the object. As a reminder, delta anything is always final minus initial. So delta L, change in the length of the object, the final length minus the initial length. Delta T, change in temperature, final temperature minus initial temperature. So, as an object's temperature changes, its length will also change. If something's temperature does not change, if you plugged in a 0 for delta T, then delta L would be 0. If you don't change the temperature, it doesn't change size. And the bigger the temperature change is, if delta T is a bigger number, the more the object will change size. So the relationship between delta L and delta T is a direct correlation. The bigger the temperature change, the bigger the size increase, or possibly decrease if it's getting colder. Since this is a delta T, I've mentioned that all the formulas for this class are designed to accept kelvins as the unit of temperature. And that is always the case. Your best bet whenever a formula calls for temperature is to use kelvins. That's just a flat out best practices statement. But, so this is an asterisk next to the blanket statement, all formulas are designed to use Kelvin. There are some formulas where you can use Celsius. Namely, if the formula has a delta T in it. Since delta Kelvin is the same as delta Celsius. The two scales are based on one another. If you increase 1 degree Celsius, you also increase 1 Kelvin because the scales are the same size. They're just offset by 273. So, in a formula like this, the length expansion formula, if there's a delta T in it, you can use Celsius as long as both final and initial temperatures are in Celsius. You can't mix and match them. You can't, since it's delta T and you have to plug in a final and an initial, you can't have one of them as Kelvin and one of them as Celsius. They have to be the same. But as long as they're the same, you can use either Kelvin or Celsius as long as it's delta T. So, the bigger the temperature increase, the bigger the change in length. And the alpha term right here is a variable that the alpha variable is how you mathematically quantify what the object is made of. Because different materials expand at different rates. For example, I'm going to tab over to the next couple of slides. This is a chart that shows various alpha constants for various materials. Alpha is referred to in this formula as the coefficient of linear expansion. And so this table shows the coefficient of linear expansion for a bunch of different materials. And if we look here, say at aluminum as a sample, the coefficient of linear expansion for aluminum is 24 times 10 to the negative sixth. Let's compare that to the coefficient of thermal expansion of Pyrex glass, which has a coefficient of thermal expansion of 3.2 times 10 to the negative sixth. Sorry, they're both times 10 to the negative sixth, but notice aluminum's coefficient is bigger than Pyrex's coefficient. This means that if you had a block of aluminum and had a block of Pyrex and heated them up by the same amount, if their delta T's were the same, the aluminum would grow more than the Pyrex did. Just based on what they're made of. The different materials just have this different property about them. And Pyrex was specifically designed not to expand very much when heated. It's engineered differently to normal glass. Normal glass's coefficient is 9 times 10 to the negative 6, and Pyrex is 3.2. Pyrex was specifically designed in order not to expand all that much, because when you're constantly putting something in an oven, Pyrex is the glass commonly used in glass bakeware, like casserole dishes. Alternatively, it's probably used in the window into your oven as well. Those objects, the casserole dishes and the oven windows, are constantly going to be changing temperature a lot. You put it in the oven, it heats up, you take it out of the oven, you dunk it in cold water, it changes temperature all the time through pretty big extremes. And it's designed to have a lower coefficient of thermal expansion so that it doesn't expand all that much when going through those temperature changes. If it did expand a lot, then it would get noticeably bigger as you were cooking with it, and then after you dunk it into cold water to wash it, it would shrink down very quickly. And an object constantly growing and expanding and contracting thermally repeatedly in a very short amount of time can wear down the object and cause it to break. There's a concept known as thermal shock, where if you change an object's temperature too quickly and its size changes too quickly, it can just break, because it is not always able to handle the stresses of changing size based on if it's attached to anything or if it's just been under a lot of stress and has a weak point in it already. This is why it's kind of risky if doesn't happen a lot in South Carolina, but if you've ever gone outside on a winter morning and noticed that your car's windows are frozen, you have to be careful about how you thaw them, because if you dunk hot water on your frozen windows, the glass of your window is going to change size quicker than if you dunked cold water on the window. And a lot of people have dealt with the problem of, if they dump hot water on their frozen windows, their windows just straight up crack because of thermal shock. The window expands more than it was safely able to handle given the surrounding temperatures, and it just breaks. So, different materials expand at different rates. Very smart engineers are able to make use of that trait or design materials that specifically do what they want them to do in this regard. And whenever you are working a linear expansion type question, and there's an alpha here in the formula, say for example you're working a sample question where you're looking at the expansion of an aluminum object. As long as the question says the word aluminum, you can scroll over to this table and look up the alpha value for aluminum. So this is a table that you will always have access to, either in your notes for homework assignments or given to you as part of a test question. It'll be either on your formula sheet or with the test question where you need it. You don't have to memorize any alpha values because there's infinitely of them. Every material has a slightly different alpha. So no memorization, you just have this table. You can access it at any time. Before we move on, I want to briefly look at the volume formula as well, which is basically almost identical to the linear expansion formula, because if we just look at the terms here, we had originally delta L over original L equals alpha times change in temperature. Here we have delta volume divided by original volume equals beta times change in temperature. Formula is structured the same way, and it takes the same logic, because linear expansion, 3D volumetric expansion, the change in volume of an object as it grows, is really just the same thing as linear expansion, just in 3 dimensions at once. If you have a cube of aluminum that you're heating up, linearly it will expand in one axis, but it also has 2 other axes that are also linearly expanding. So the volume expansion is just linear expansion, but in every axis at the same time. So the formulas are nearly identical because they work on the same logic. So the change in volume divided by the original volume equals beta times change in temperature. The primary difference is that the constant used here, the coefficient of volume expansion, is called beta instead of alpha. And every different material has a slightly different beta, like every different material has a slightly different alpha. this same table right here, this column is alphas, and this column is betas. So this second column, average coefficient of volume expansion, shows the beta constants for a bunch of different fluids. And one factoid that I would point out to you, I'm going to tab back to the explanation slide here. Since volume has 3 dimensions and length is only 1 dimension, all beta values, so say you look on this table, all beta values are equal to 3 times their corresponding alpha value. So for example, say you were wanting to know how much the volume of an aluminum cube would expand when you heat it up. This particular table doesn't list the beta for aluminum, it lists the alpha for aluminum. But all betas are equal to 3 times their corresponding alpha. So if you needed the beta value for aluminum, you could take the alpha and just multiply it by 3, since it's growing, changing length in 3 dimensions at once. So that's the relationship between alpha and beta. If this table has, if you're working a question and you need to consult this table, if it doesn't list the specific one, alpha or beta, that you need, you can take the other one and convert it into the one that you need. It's worth keeping in mind. Let me know if there's any questions or issues thus far. Whoops. And I'd like to make sure we look at least one quick example before we end up breaking for the day. I've mentioned the expansion of aluminum objects a few times, so we're going to look quickly at such an example. So let's say that you have an aluminum pipe and you're going to measure it with some measuring tape. At the starting temperature of 21.1 degrees Celsius, the pipe is 18.7 meters long. What length do you measure when you increase its temperature to 29.4 degrees Celsius? So we have our starting length, the 18.7. We have the information for our temperature change. We go to a final of 29.4 from an initial of 21.1. And we know what our object is made of, specifically aluminum. So we have all the information we need to use our linear expansion formula, delta L over original L equals alpha times delta T. In my work here, I've made use of the fact that delta L is really just L final minus L initial. So I've converted delta L into LF minus LI. The LI is the 18.7. The LF is what we're solving for. We want to know what the final length is. So that's going to be the remaining variable at the end that we solve for. So LF minus 18.7 divided by the same original length, so we're going to reuse the 18.7 there, is equal to alpha, specifically the coefficient of linear expansion for aluminum. So we know it's aluminum, we know we need aluminum's alpha, so at that point one could tab to this slide and consult this table. Please use this table on all homework assignments. You're allowed to have it loaded up. You can use it to your advantage. Coefficient of linear expansion for aluminum is 24 times 10 to the negative 6th. So that is the number we will plug in for alpha. And then lastly, delta T, 29.4 minus 21.1. As I said before, as long as it's a change in temperature, you are allowed to use Celsius, as long as both units are in Celsius. And that's all of the separate variables. We can perform some algebra to solve for LF. I would multiply both sides by 18.7 and then add 18.7 to both sides. Please let me know if you're having any issues reaching this answer if you work through it yourself. And our final length, this is the expanded length, is 18.704 meters. That means that the delta L, the actual change in length, if we compare this to the original length, we only expanded by 0.004 meters. That's an increase in length of 4 millimeters. So our answer is correct. This is the change in length that this particular object would undergo. It's just not a very big change, I will admit. And this is a pretty big object to start with. 18.7 meters long is very long. A meter is just bigger than a yard. So this is possibly about 20 feet long. Sorry, no, about 20 yards long, about 60 feet long. So not a small object, and it only just barely grew when the temperature changed about 8 degrees Celsius. So this is one reason why you tend not to notice thermal expansion except in a few key instances, because most of the time the temperature changes cause inconsequential size changes. But when in the few instances where any change in size can cause catastrophic failure, suddenly even growing this much can become a problem. I've mentioned already roads cracking, buildings falling over. There's a picture within this slide that is here to help demonstrate this purpose. I mentioned what happens when roads and bridges don't factor in thermal expansion, and when they don't factor in thermal expansion and the objects in question don't have room to grow when they inevitably grow, you end up with stuff like what's happening to these railroad tracks. And for comparison, there's a set of straight tracks next to it. These tracks expanded thermally, and frankly, railroad tracks are going to change temperature pretty rapidly because they're made of metal. They're sitting in the hot summer sun a lot, and whenever a train rolls over them, they're going to absorb thermal energy from the friction of that interaction as well. So railroad tracks really deal with some very high temperatures and a lot of big temperature changes. And on hot days, if the tracks don't have any built-in mechanism to handle thermal expansion, you end up with stuff like them warping like this, because they're going to grow. All objects will when heated. If there's no space, they'll start bending and buckling and warping to a ridiculous degree. It's also worth keeping in mind, I'm going to tab back to look at the formulas. This is the linear expansion formula, just slightly rearranged. I'm normally presenting it as delta L over original L equals alpha times change in temperature, but it is legal to multiply that original L in the denominator over to the numerator on the right side. So just to compare the original to this modified version, note that delta L, the change in length, is proportional to what the object's original length already was. So if you had a bigger starting length to begin with, the change in its size will be all the more drastic. So delta L scales not only with delta T, but it also scales with the original length. So the bigger the object was to start with, the more it will grow when exposed to the same temperature change. And this is particularly egregious in really long objects like railroad tracks that stretch on for literal miles. So not only are they exposed to constant major temperature shifts, they're also just really long, and therefore their growth will already be more than a smaller object made of the same material exposed to the same weather. So, like I said, this can be catastrophic if architects and engineers don't consider it and don't work in fail-safes for what's going to happen when the change naturally occurs. I think, like with bridge and road beds, a lot of modern tracks, to avoid this, will put spacers every so often within the rails. I haven't been on railroad tracks recently, but I think occasionally there's just a small little like break in the tracks that's shaped kind of like a letter V, so that kind of like the teeth on the metal gap teeth on the road beds, there's space for the pieces of metal to expand into each other, but also the shape of that V means that there's always a surface for the wheels of the train to be on. So I think that's how most modern rail companies handle that problem. So it's about 10:30 now. I'm interested in how you guys feel, how this information is processing for you. If if no one has any specific questions, then we can break here for today. Like I said, we're going to stop around now. And if there's nothing specific from you guys, then I recommend keep using these notes, specifically the change in volume and the change in length formulas. Keep working on the homework over the weekend. We'll work some more examples in class next week. There's specifically going to be at least one more. There's at least one more thermal expansion example within the notes. It combines thermal expansion with some trigonometry. As such, I've already the pre-recorded lesson that I mentioned to you earlier has me working through that example in it. So if you're working on the homework over the weekend and you just want to see how a problem like the one in the homework would go, you can consult the video lecture and the notes on that one, or you can ask me questions. And next week we'll reconvene, talk a little more about thermal expansion, make sure everyone is cool working through that next example. And I think the last major topic within Chapter 10 specifically is going to be about gas law, namely how gases expand and contract due to temperature change. So, are you guys feeling all right now? And does anyone have any questions before we break for the weekend? Okay. Fantastic. Well, do work on the homework whenever it's convenient for you. We will reconvene Monday, and if you have any issues or questions over the weekend, please email me. I will reply as soon as possible, I promise. So until then, see you guys, and have a good weekend.